Hi.
Hello. Hi,
This
Daniel.
one?
Yes, yes. Yeah, okay.
All right, let's go. We're back.
Let's go. Good.
Okay, screen share. All right, this work?
Yeah, that's good.
Okay. Let's go back to capacitance. We've passed this part.
Right. So do you understand the slide before this? And I was telling you that's only charging, not discharging. That's where the
Yeah.
slide ends. Not the one after this, the one with a lot of words. One a lot of words. Right. Yeah, this thing. This thing is just charging. Are you happy with this slide?
Yep.
For example, you have a question mark below there. Are you okay?
Yeah, sorry, it was a while back. So energy is being stored. Because what's the mechanic called? So essentially, the
Essentially,
battery
electron, right?
was
The battery send electron to the from negative to negative, right? So that plate stores the negative charge, right? And then the battery suck or take electron out of the positive one. So that one become positive. So one send electron, one take electron. That's just how they do it. Very simple. Don't say send charge, just say send electron and also absorb electron. Both is happening at the same time, right? Send electron and absorb electron at different plates.
Does that work? To and from the plates.
Yeah. Are you okay? Are you okay with that?
Yeah.
Okay. So if okay, let's. If you're okay, then you move on, right? He goes on to. He goes on to continue it's in a good detail, I suppose. He goes on to explain why it stops charging.
The second electron to move will find it slightly more difficult. Why?
Because the first electron repel. Yes, correct.
Repulsion.
Makes sense, right? Another way of saying is that the plate already gained some voltage, and that voltage is opposing the sending voltage. That's
Okay.
explanation, I think, even makes more sense. Look good.
More energy.
So increases, and that's how you finally stop. When you have too much of an electron, you can no longer send. That is where the voltage is the same.
Until there is insufficient potential energy available in the cell. So it's like it ramps up. It's like, like that.
Right. And then you go on until the ramping up is not like that. That means you're ramping up to infinity. You ramp up in the other curve. You ramp up to a horizontal. The ramping up is like that. It's exactly like this. So you're gonna go to an asymptote, to a finish line, something like that.
Okay.
If that makes sense, right? So the later paragraph, the last paragraph, I think you should be able to understand by now.
If we were to disconnect the cell, measure the potential difference because of the VDC and stuff.
I hope this makes sense, right?
Charging the Yep.
So the battery charges the capacitor. Yep. More likely, the battery is cloning itself to the capacitor. It's
I don't
more
think
like
they would
that.
accept that in the exam.
But we never bothered about formalities right now.
Yeah.
The point is, capacitor is a small power bank. Right? Okay, let's move on. He goes to a formula, and this is hopefully the only formula that you have to worry about, right? Hopefully lah.
C is Q heavy.
C is the new thing, capacitance, not Coulomb. Yeah, Coulomb is the unit of the charge. Be careful, those two C can be very confusing.
Yes.
Look at the final paragraph. There's one C there. What is that big C? What is that big C? Is that big C capacitance or is that big C Coulomb?
Coulomb.
I think it's very annoying if you cannot differentiate, right? It will be very
This
annoying. That one C.
That's Coulomb.
Very good. So that means that belongs to the Q, right? The charge, right? So just want to say that. Right, just want to say that, right? The farad is new, right? But the Q and the V is not new, right? So let's move on. Let's see how you use it, lah. Now, microfarad and millifarad is more common because you never use 1 farad. 1 farad is just too big, lah.
What's the units for this? Like 10 to the power of
3. Milli is
minus 3.
Micro minus 6. You need to remember this. Yes, very good. And pico is minus 9. No, I'm sorry. Pico is minus 12. He missed nano. Nano is minus 9. I don't know why your slide has this thing. That's not good. Nano is minus 9. Write down nano. No, not there. In between micro and pico. In between. Oh, the most appropriate one is picofarad. Yeah. But nanofarad, no. Even millifarad is good. So they are not intentionally annoying you by using picofarad or nanofarad later. They are not. Because that's the more common capacitance for AC.
Maybe
Remember?
NF like that.
Yeah, NF, and then minus 9. You see in your next work example, you'll be using nano already. See that? Nanofarad. And this is a more normal capacitance of a capacitor to use for smoothing out AC load. It's common. Yeah, that's why.
Milli, micro, nano, pico.
Yeah, more nano and pico. More nano and pico. Okay, so very good. The first example is just applying formula, not the most. You have microfarad, right? Good, microfarad. Right, so just don't forget that.
Manipulation of
simple stuff, right? This is important. Could you just take it as necessary? Just take it, the energy is QV, because you're supposed to know this. You're supposed to know that energy can be Q times V, but they usually call it work. Work is equal to QV back then in DC circuit. So if you think that this is new, then think of it as somewhat important. You need to do. Looks like there's a lot of slides. Maybe we can cover a bit more. Calculate the energy. So yeah, obviously you're just using a formula, right?
Yeah, I tried to do it by myself, just like that.
Now looks good to me.
Yeah, correct answer.
All right. MF or now he goes to
this is confusing.
Okay, let's stop here. Right. Okay.
You know it's EMF, right? Just
no. That's the problem. E0 is not EMF. That's a big problem. So EMF symbol is this. It's very annoying that E0 is not EMF. Very annoying. That E0 is what you call the E0 that you see in the field, the electric field. Remember, the small k is 1 over 4 pi E0.
It's a constant.
It's a constant. Just go and look at your data sheet and please confirm that E0. They don't even mention it here. It's annoying. They don't even define E0. Why does your slide do this? The permittivity of free space. Yeah, he did. The permittivity E, right? So E0 is the permittivity of free space. That means the permittivity of vacuum. E naught is the permittivity of vacuum.
Where is it?
See, this insulator of permittivity epsilon, right? So this epsilon naught is permittivity of vacuum. The naught denotes vacuum. So when you're not using vacuum, but insulator, right? That means you say insulator means no longer vacuum. That means in between the plate, they don't usually put it as vacuum. That's not efficient. They usually put insulator instead. That means something which is not conducting, right? So please type that. Insulator means no longer vacuum. So no longer E naught law, just epsilon, right? So some other number law.
Value is.
The value is whatever that the insulator is made out of. So we'll see later.
8.854
times 10 to the power of minus what 7
12.
minus
12.
Okay. Whatever the unit is, right? Okay, there you go. So given lah. More importantly, please write this down as given, no? So that you know that it is given.
Sure.
Right? So insulator of permittivity means it's no longer vacuum. So it's no longer epsilon naught. It's epsilon something lah.
Wait, this is the part I'm confused about. Because I don't think I've seen this before.
Yeah, so the parallel plate is exactly how we describe the capacitor at the start. You know, one plate disconnected from another plate, right? Remember, that was how we discussed capacitor. Parallel plate capacitor was what we have been discussing from the start. There's nothing new here. Do you understand? I don't think it's at topic 10. I'm very confused. It's the first time you see this is at 11.2. I'm a bit confused with topic 10. I don't know what's going on. Oh, topic 10 must be electric field, right? They might have talked about, they talk about parallel plates in electric field, but they don't tell you that that's a capacitor. So either refer to 10 and electric field or just refer to 11.2 or 11.3, same thing. Parallel plates are capacitors. That's fair. That's fair. I think this is correct. Okay. I think that's what you mean. So is a parallel plate a capacitor? Yes.
Yes.
Parallel plate will always function as a capacitor. There is no escape from it. The parallel plate will forever be a capacitor.
As long as there's a non-conductive material in between.
Plates.
Right,
yes,
that's the...
okay. Correct. Right. But there must be a plate lah. That means it cannot just be wire. Then too small of an area.
Okay.
But will a capacitor always be a parallel plate? Well, that's a more complicated answer. But
does it have to be parallel?
It has to be facing each other. So you can argue that therefore it is always parallel. It is always parallel.
They could be like a bit off center.
There is no point in slanting them though. So I mean,
so it's a mechanical error. Like one is like that. It will still work.
It will still work. It will still work.
Is there any? Does it affect the performance?
The distance matter. The amount. That means even if it's vacuum, you call that you still call that the amount of things in between. So it does matter. It does matter.
Okay, that's matter. But
you probably wouldn't go into that. Probably not. Probably you just assume that this is an ideal world where everything is parallel. Okay, so you go to the final. Go to the last paragraph. No, not final sentence. Last paragraph of this slide. Are you okay? It's not always vacuum. It can be filled with insulator. It just makes more practical sense to use insulator instead of vacuum.
Oh.
Vacuum is very difficult to maintain. Very difficult. So we use insulator instead. So the epsilon naught is no longer epsilon naught, just epsilon. It's some other value. Look. So okay, I mean, yeah. Okay, so the way to increase the bottle, right? The bottle capacity, right? Sometimes we want a bigger bottle, sometimes we want a smaller bottle. So I think the first one very obvious, right? The first one is very obvious. I want the area to be bigger. Right. The setting the plates closer together is a very weird and non-instinctive thing. So if you want to make the bottle bigger, you make the plate closer. This is correct. They don't discuss why. It's very counterintuitive. It's very counterintuitive. Yeah, see, the sentence below also never explained. It's very weird. For now, just take it like this is too weird. Number one makes sense. Number two, weird. Number three, depends on how you see it. It's if you don't make it vacuum, it actually increases the capacitance. It's very weird. You fill the bottle with something else, then the bottle capacity increase. You can also call it counterintuitive, no? Right? You can also do that. But that does happen, that does happen.
But it kind of trails off at the last sentence.
The new material can, let me see,
It doesn't continue on the next slide. It just gets cut off.
There. It is explained by the next step. Next step. Go down. So as you can tell, the between the plate, you see the plate now, right? The between the plate is no longer a vacuum. Okay. The insertion of dielectric. Dielectric is suddenly a new word. The dielectric is the insulator. No? So how come the insulator suddenly changed word to dielectric? Because dielectric describes what the material does. So the dielectric. So one more time, the dielectric is the insulator between the plates. Just write that down first. It is. But dielectric means it's almost like a magnet. Like remember when you put a soft iron between two magnets, the soft iron become magnetic, correct? Remember? That's how you can magnetize a soft iron very easily. Just put it between two magnets. Now, dielectric is the same thing. You're putting it between two plates, positive and negative. The guy in the middle, this dielectric material, also become positive and negative. That's the word dielectric, positive and negative. That's all. That's all. See, the dielectric gets to become positive and negative. Very similar to how magnet magnetize an iron core. That's all. That's all. It is still non-conducting, by the way. It is still non-conducting. Are you okay so far? Do you understand what I'm saying? See, some of the stored energy of the capacitor has been used to align the dielectric molecule. That means if you don't put positive and negative, the dielectric molecule is not aligned. Same thing like the soft core iron with magnet. The soft core have magnetic particles inside, but if you don't put it in a magnet, they are not aligned, so they are not magnetized. The point is, because the plate align the dielectric molecule, you increase the capacity of the bottle. See, dielectric increase the capacity. By filling it, you're actually increasing the bottle. If it is counterintuitive, go ahead and write that down.
Okay, I kind of get it. It acts like a medium.
Yeah, and the medium kind of takes more energy to do, so you can therefore put in more energy, kind of.
Okay.
By the way, it is always an insulator. Just saying, it is always an insulator, right? Because it can never be a conductor. Yeah, I think for our normal person mind, I don't think we can imagine what a dielectric is. It's a very non-practical material. Like, how am I supposed to imagine that plastic is dielectric? I have absolutely no idea. It doesn't work instinctively. Okay, so we have 4 more minutes. You're studying quite fast today. Still very happy.
It's because
John,
I read through it yesterday. So
good, very good. It works, right? It works, right? Now, do you understand the
yeah.
slide before? That's just the design of the capacitor. So parallel plate, you roll the plate. You
I've
understand?
seen it
You
before.
roll.
I just don't know what it. I didn't know what it was.
So you can accept the fact that rolling the plate, saves space, right? That's what we are doing here, lah.
Okay.
All right, go. So that's your E over E naught, meaning the comparison between epsilon of a something and vacuum lah, vacuum. Now, as you can tell, ceramic 15,000. That means you're increasing the capacity of bottle by 15,000. That's good lah. That's good. That's good. Right, so they just apply this or whatever. So we are obsessed with increasing the capacity of the bottle so that we can make the bottle smaller. I think that's the idea here, no? Making the bottle smaller will make everything smaller, which is good. We like that.
C is E naught A over D.
That was the formula just now, right?
8 point. This is
That's
E
your
naught.
permittivity of free space. Yeah.
This is A.
Area, right? In meter square, and that's the distance between the two plates, right?
And the F is farad.
Is farad, which is the capacity of the bottle. That's a picofarad. You notice that? There's a pico.
Oh, so this could also equals to 5.9
picofarad.
PF.
Right. So picofarad is a working capacity lah.
Pico is a different.
Up. Wait,
oh, okay. So only microfarad has the weird thing.
Yeah, as what do you call it? The Greek word lah.
Mu, right? Mu.
Mu, yeah, the Greek word lah. Correct.
Not wrong. Yeah.
Okay. The rest, no.
All right, pedestrian dielectric concentrate, which means
now you increase the capacity by 3 times, right?
Okay.
Which is nice, right? You want that. Right? Number 2, I mean, simple stuff lah. I mean, 1.1 meter square. He make a mistake again. It's supposed to be area. 1.1 meter square. Right. Just kindly point this out to your teacher nicely so that your class benefit, if you could do that. Okay. Just kindly. So series in parallel will be counterintuitive also. The series of capacitor works like resistor in parallel, vice versa. It is mind-boggling or mind-warping. It's weird. So you have 2 options, which is to understand them. It can work, or you can just memorize. So that's totally up to you. But we are at 10. We're at 10 o'clock. We're at 10 o'clock. Let me just see how far you want to discuss. Can I do that? Can you just give me a few the other side? This, okay, then go on, right? You want this, sure, go on, right, that's fine. Discharging, charging, sure, go down. Then finally he has this. He put this at the end. Goodness me, this is supposed to be the most important formula. Hi. Okay, go down. Why did he leave it behind? Go down. This takes a long time. Okay, so the 2 main section is the parallel and series capacitor. It takes around 3 slides. Just take it as you just have to memorize it. It's mind-boggling, but it's just a reverse of resistance, because the next 5 slides is the time constant is traditionally in polytechnic. That's the most important thing, because that's where the practical application comes in. I don't know how your teacher will focus on the last 5 slides. So I don't dare to dismiss it. Turns out that it's there. Right? We'll cover it next time. Okay? We'll cover it next time.
All right.
Okay? We should pay more attention to the time constant. Unless unless somehow your teacher kind of dismissed them, which is, I don't know lah. I don't know what he will do lah. Right? I don't know.
Okay. Also, next Sunday I won't be in Singapore. Wait, this Sunday I won't be in Singapore.
Like, that's I hope you're having fun. I guess no.
Yeah.
Right. Okay.
Do you want to call anyways? I can call. I can make time at night because I'll be in Thailand.
I don't
but-
mind since it seems to be still very beneficial. Right.
Okay,
don't mind.
I will update you. Actually, I can update you now. I just go check the schedule.
Right. The more important thing is whether the connection there can make it or not lah.
Let me
You
just
wouldn't
put
know until there.
Wi-Fi
You
lah.
wouldn't know, right? You will find out there, lor. So yeah, lah. Yeah. No, please do that. I don't mind. I don't mind.
Should be able to call at night, probably closer to 8 nah. I think on Sunday. Is that okay with you? 8 to 9?
8 to 9. Let me think for a while. Your supposed time is, what was it? Oh my goodness, 6 to 7:30.
Let me see, yeah.
Right, supposedly, right?
I'll
No,
be in
well, no,
Bangkok.
6:30. Sorry, 6:30 to 8. Yeah, we were discussing that. So it's 6:30 to 8. 8 to 9
Yeah.
probably too packed already. Like I told you, Sunday is a very
Okay.
packed day. So if you can call only at 8 at Singapore time, I don't think that works lah. It's a
8
timing.
Singapore time will be 7 for me, so I don't think I can.
So if you're supposed to call at 6:30, then you're calling from there 5:30 low. Can you do that?
Yeah, cannot lah. No, I did not want.
Right. Then what to do? Have fun. Have fun
Okay,
first, lor.
if I can, I will update you lah.
Oh, please
see
do.
how-
Please do. Right. I'll be happy. Right.
All right. Okay.
All right.
Then.
Good job for today. All right. I'll
All
see
right,
you.
but just assume I'll see you next Tuesday lah.
I think
For
we
now
should
lah.
assume that lah. I think we should assume that. Huh?
Yeah.
I think we don't want to